start na?
Get ready, get set.
Hello! Hi! Welcome as we deep dive on the try algorithm. If you've ever wondered how search engines predict what you're typing or how your phone knows the next word, this is it.
Stay tuned. Interesting kay ni.
Girls, naka-try na ba mo og autocomplete? Kaya kining work kabalo na imong phone kung sa sulod nga i-type?
Siyempre, nindot kayo kay convenient. Kabalo ba mo nga tries ang gamit ana?
Try? As in, try and try until you die?
Close! Actually, a try is a tree for trees.
What is a try algorithm? A try, short for retrieval, is a tree-like data structure that stores strings. Each node in a try represents a single character, and words are stored by branching through these characters from the root down to the leaves. Let's say you have these three words: cat, car, and cap. Instead of storing each word individually, a try lets you reuse the common prefix CA. Then the paths diverge into T, R, and P. That's how tries save space and improve performance. The key advantages of tries include: first, fast lookups. Time complexity for searching or inserting is big O of L, where L is the length of the word. This means the time it takes to find or insert a word depends only on how long the word is, not on how many words are in the try. For example, searching for car will take exactly 3 steps: one for C, one for A, and one for R. This is faster than a binary search tree or hash table in some use cases, especially when many words share prefixes. Second, prefix searching. Easily find all words starting with a given prefix. Since tries are built around characters and shared prefixes, you can quickly locate the node corresponding to the end of a prefix. From there, a simple traversal of its child nodes will give you all the words that start with that prefix. This makes tries ideal for autocomplete features or dictionary suggestions. Third, alphabetical ordering. Tries naturally store words in lexicographic order. Because child nodes are typically stored in alphabetical order, traversing the try from left to right will output words in dictionary order. This eliminates the need for an additional sorting step, which is beneficial when displaying search results or organizing data alphabetically. These properties make tries useful for autocomplete systems, dictionaries, word games, and even IP routing. We'll dive deeper into all of that, but first, let's understand its structure.
So, every letter has its own node?
Yes. Imagine a root, then every branch is a letter. If you insert cat and cap, they both start with CA, then split sa T og P.
So, usay na as a node.
A character, a child node, or a flag nga mag-indicate if end of word na siya.
Let's talk about the 4 main operations we can perform in a try. Insert, search, starts with, and delete. Each of these has a specific purpose, and they work together to make tries really efficient for handling dynamic sets of words. So, let's start with the insert operation. When we insert a word into a try, what we're doing is building a path for each character of that word, one by one, starting from the root node. Here's how it works. First, we begin at the root of the try. Then, for every character in the word, we check if that character already exists as a child node of the current node. If it does exist, we just move to that node. If it does not exist, we create a new node for that character and then move to that new node. Once we've processed all characters in the word, we need to mark the last node as an end of word node. This tells the try that the full word ends here, not just a prefix. Example, let's say we're inserting the word dog. We'll start at the root, then create or move to the node for D, then O, and finally G. Once we reach G, we mark that node as an end of word, meaning the word dog has been fully inserted. Next is the search operation. This is used to check if a given word exists in the try. Here's how search works. Again, we start from the root. We go through each character in the word and follow the path in the try. If at any point a character is missing, meaning there's no child node for it, then the word does not exist in the try, and we return false. If we successfully reach the last character, we then check if that node is marked as an end of word. If it is, we return true. The word exists. If it's not, that means the characters might be there, but they don't form a complete word. It's just a prefix, so we return false. Suppose we search for the word doll in a try that only contains the word dog. We'll find D and O, but there's no L after that, so the search will return false. Doll hasn't been inserted. Starts with. The starts with operation is similar to search, but it's more relaxed. Instead of checking for a full word, we just want to see if any word in a try starts with a certain prefix. Here's how it works. Just like in search, we start at the root and follow each character in the prefix. If all characters are found and we can follow the entire prefix path, we return true, because at least one word starts with that prefix. We don't need to check if the final node is marked as an end of word. Example, let's say we call starts with do in a try that contains dog and dove. We'll follow D, O, and see that the path exists, so we return true. Both dog and dove starts with do. Now, delete is a bit more complex than the other operations. The reason is, when we remove a word, we have to be careful not to accidentally delete parts of other words that share the same prefix. To delete safely, we usually use recursion. We start from the root and go down the word's path. Once we reach the end of word node, we unmark it. We say, this is no longer a complete word. Then we go backward, or recursively backtrack, and check if each node along the path has no other children and is not marked as end of word for another word. If both conditions are true, we can safely delete that node. But if the node is still being used by another word, like a shared prefix, we leave it alone. Example, suppose we want to delete dog, but we also have dove in the try. We can unmark G as the end of word, but we shouldn't delete D or O because they're still part of dove. These four operations, insert, search, starts with, and delete, make tries extremely powerful for storing and handling words, especially when the dataset is dynamic and changing. They allow for fast lookups, efficient prefix searches, and safe deletions even in overlapping word cases. That's why tries are commonly used in things like search engines, auto-suggestions, and dictionaries. Basically, anywhere you need to manage large sets of words quickly and reliably.
Okay, mag-insert ka. Bat, ball, bark, and band.
So, third yun ang B and A, then different paths for the rest, no?
Tama! If we search for bark, then we follow the path B, A, or K. If marked as any word, then found na.
What if bara?
If wala siya na mark, then it's not considered a full word.
When analyzing the time complexity of a try, we typically refer to L, the length of the word being operated on. Best case. The best case occurs when the word or prefix we are searching for diverges early from other branches in the try. In this case, the lookup or insert operation might finish in fewer than L steps, say in just a few levels. However, we still express the best case as big O of 1 when the prefix mismatch occurs right at the start. Average case. In general usage, where words are of moderate length and the try is balanced with a fair distribution of characters, the average case time complexity for insertion, deletion, and lookup is big O of L. Each character in the input word is processed once, and each operation moves from one node to another in sequence. Worst case. In the worst case scenario, especially in an uncompressed try, where each word is completely unique with no shared prefixes, you might have to traverse the entire word from the root to the leaf. This leads to a time complexity of big O of L. Additionally, space complexity could grow large if many distinct words with little overlap are stored. In all cases, L refers to the length of the word being searched, inserted, or deleted, not the total number of words in the try. This makes tries very efficient for operations involving string prefixes, regardless of the size of the overall data set.
So, compared sa hashmap, mas maigid ang try for prefix-based tasks.
Pero mas intensive memory siya if sparse ang data.
True, pero na-compress tries like radix trees to help reduce space.
As always, piliin mo based on what sa imong need.
When to use a try, key scenarios, and trade-offs. So here are the best uses for a try. Number 1, a try is ideal for autocomplete and predictive tasks. It quickly finds all words with a shared prefix. For example, typing uni suggests universe or university. It's used in search engines, messaging apps, and IDE code suggestions. Next is avoiding hash collisions. So no need for hash functions. Strings are stored as paths in the tree. Now, when to skip the try or when to avoid a try. First is limited memory. Tries can use more memory than hash tables or BSTs. For example, storing apple and app requires separate nodes. Number 2, exact match queries only. So if you really need prefixes, a hash table is simpler.
So ready na ka mag-go to try, Marvin?
We're ready na kayo. Salamat sa explanation, girls.
So mga viewers, we hope you learned something new today.
Keep building and always stay curious.